Templates are the way that C++ implements genericity. Genericity meaning that you write a piece of code once and it can be used in a variety of contexts. There are generics in C# and in Java, as well as some other languages, different names for the same concept. However, templates are fundamentally different from just about everybody else's implementation. Templates are resolved at compile time, not at runtime. This has some benefits and some drawbacks. The number one benefit is speed. All of the performance hit is taken at compile time. There is zero performance hit at runtime. The compiler actually generates versions of the code for the various types that you're using it with. In languages that do runtime checks, everything happens at runtime. There is a performance cost at runtime. This may give you a little more flexibility. It does, however, slow your application down. A generic-based solution can never be as fast as a template-based solution. The idea is that you write something, maybe it's a class, maybe it's a free function, and it can be used with a variety of different types. Imagine math work like finding the largest something. Could be the largest integer, could be the largest floating point, could be the largest bank account. Finding the average of a whole pile of things, or keeping a collection. An ordinary array, a linked list, a queue, a hash table, a dictionary, every data structure probably that you learned as an undergraduate. You can have a linked list of integers, or a linked list of floating points, or a linked list of bank accounts, or a linked list of employees, and it doesn't really matter. The code about keeping track of the next node and the code for insert and the code for delete is identical regardless of what it is that you keep in there. But these are type-safe collections, meaning that if I have a linked list of employees, I can't add a bank account to that list. Type safety is a huge part of C++. This is how you achieve a type-safe, high-performing collection and algorithms that work across those collections, sorting them, searching them, that kind of thing. Operator overloads are a big part of how many of these templates are actually implemented, and that's what makes it easy to mix and match so that the same code can be used for, say, integers and bank accounts. I find that other languages tend not to do that. Their general solutions often can only take user-defined types and not the fundamental types. They often rely on the existence of member functions with names like add or compare that are not defined for fundamental types like integers. Using operator overloads gives you compact code and highly readable code. It is also what makes the same templates work for both fundamental types and user-defined types. We've mentioned the standard library a number of times throughout this material, and I'm sure you're already convinced that it's full of rich goodness, even though all we've really seen so far is strings and writing to the screen and reading from the keyboard. The old name of the standard library was the Standard Template Library, or STL, and old school C++ developers like me still often call it STL in casual chit-chat. Yes, I have casual chit-chat about compiler libraries. It's who I am. It's rich in templates, collections, algorithms, and a lot more besides. And as you move forward along your C++ path, you're going to meet a lot of the things in the standard library, and you'll understand them better if you understand templates.